In today's video, we're going to be looking at inverse trigonometric functions. So we're going to be looking at the inverse of sine, cosine, and tan. So I want to look at first the graphs of each of these so that we can get a feeling for what the domain and range of these inverse functions is going to be, because that is very important whenever we look at these inverse functions. First, let's look at the inverse of sine. The inverse function of y is equal to sine x is y is equal to the inverse sine x. With these inverse functions, remember for sine, we input an angle and we get out a value that's between -1 and 1. With these inverse functions, we are putting in a value that is between -1 and 1, and our output is going to be an angle. Whenever we use these inverse functions, we always do everything in radians. So normally it's going to be something in terms of pi, but it's always going to be in radians. So bear that in mind. Our input here is going to be between -1 and 1. So our x values are between -1 and 1. And our y values, our output values, are going to be an angle that's in radians. The issue that we have here is that our original function, y is equal to sine x, is not 1-to-1. When you sketch out that graph of y is equal to sine x, I'll just do a quick sketch. It will look something like this, and it will keep going, obviously. Well, this is 0, this is pi, this is 2 pi, this would be -pi, etc. Okay, this is not 1-to-1 because for various different x values, we end up with the same y value. So this thing is not 1-to-1. And in order to have an inverse function, we need to make it 1-to-1. So what we're going to do, like we did in some of those inverse function examples before in our previous videos, in order to get an inverse function for sine, we're actually going to restrict its domain. And for sine, it's going to change for cosine, keep this in mind. But in order to restrict this domain, I'm going to restrict it to between -pi/2 and pi/2. So I'm just going to be looking at this section of the graph here. So in order to make it 1-to-1, I'm just going to restrict this domain to between -pi/2 and pi/2. Okay? Because within that domain, within that restricted domain, sine of x is 1-to-1, and therefore I can find its inverse. So let's draw out that portion of the graph so that then we can actually graph the inverse of sine. Okay. So our original graph of y is equal to sine x on that restricted domain would look something like this, where this is pi/2 and this is -pi/2. If you remember, in order to draw an inverse function, we take the original graph and we are going to reflect it in the line y is equal to x. Okay, so you go ahead and you can dot out that line of y is equal to x, and then you can go ahead and actually draw the graph of inverse sine. So if you were to draw that, it would look something like this. Like I said, this is just a sketch here, but it would look something like this. Okay. There is a really good picture of this in the textbook if you want to go ahead and check that out. But in the red, we have y is equal to sine inverse, and then in the black, we have y is equal to sine of x. Now, because we have a restricted domain for sine, that now means that sine inverse also has a restricted domain. So let me draw this out. The restricted domain of sine x was between -pi/2 and pi/2. So that means that my range of the inverse sine is between pi/2 and -pi/2. What about the domain of sine inverse? Well, I know, going back to my graph of sine, I've got that domain of negative pi over 2 to pi over 2. I still have a maximum of 1 and a minimum of negative 1. And it's actually at those endpoints of the graph is where I get that value of 1 and negative 1. So that now becomes my domain of sine inverse. So that tells me that the values that I can plug into sine inverse are going to be between negative 1 and 1. Okay. So that tells me that my domain of y is equal to sine inverse x is negative 1 to 1, and we're going to include those values. And then the range of sine inverse is going to be negative pi over 2 to pi over 2, again including those values. Okay, so my restricted domain of sine has now become my range of sine inverse, and my range of sine has now become my domain of sine inverse. Please keep this in mind. We will come back to this in a bit when we do some more examples of working with these trig functions. But please remember that for sine, my range is between negative pi over 2 and pi over 2. If we look at that on a unit circle, negative pi over 2 is found on that negative y-axis. Pi over 2 is found on the positive y-axis, and we can go between those two values. That means that my output of sine inverse, so that y value, my range, is going to land somewhere in quadrant 1 or quadrant 4. Okay, and we are going to make those angles negative. So anything in quadrant 4, we're going to treat it as a negative angle. It will be coterminal to a larger positive angle, but we are just going to be dealing with those negative angles that are between 0 and negative pi over 2. Again, everything's in radians. Now let's look at the inverse of cosine. So that's going to be y is equal to cosine inverse x. Okay. Again, we have the problem that cosine is not 1 to 1. So when you look at the graph of cosine, again, I'll sketch a quick graph here. Okay. And I'll carry on this way as well. Okay. You've got 0, pi over 2, pi, 3 pi over 2, 2 pi, and again in the opposite direction it's going to be negative pi over 2. It's not 1 to 1 because for one y value we have multiple x values, as you can see across that horizontal line. So we need to restrict its domain in order to get the inverse. What we do for cosine inverse is we are going to restrict the domain to be between 0 and pi. Okay. On that restricted domain, this function is 1 to 1. So then we could go ahead and find the inverse for the function on that restricted domain. So let's go ahead and again graph this, and then we can look more at the domain and range of cosine inverse. Cosine inverse works very much the way that sine inverse did. You're going to input a number that's between negative 1 and 1, and you will get out an angle. Okay, so let's go ahead and draw this. So we said that we're going to restrict the domain to be between 0 and pi. So there's 0 and there's pi. Again, you can dot out the line y is equal to x, and then you can go ahead and find that your graph would look something like that. Again, not completely accurate, but you can see if you go ahead and look in the textbook, they will have a more accurate picture for you. But the main thing that we want to look at here is the domain and range. So our domain for cosine was restricted to 0 to pi. So that tells me that my range of cosine inverse is going to be between 0 and pi. Then my range of cosine is between -1 and 1. So my domain of cosine inverse is going to be between -1 and 1. Again, not completely accurate on this graph, but we just want to look at what that domain and range will be. And as I said, you can get a more accurate picture of this if you look in the textbook. So our domain of y is equal to cosine inverse is going to be the range of cosine, which is -1 to 1, and the range of y is equal to cosine inverse is going to be that restricted domain that we had for cosine, which is going to be 0 to pi. So this is where you need to remember that we are going to have a different range for sine inverse and cosine inverse. So please keep that in mind, which way around it is, as it is very important when we go ahead and do some problems where particularly both of them are involved. Now we're going to look at the inverse of tan. So y is equal to tan inverse x. Okay. What does this graph look like? Well, again, we have to restrict tan to a particular domain, because if we did tan over the whole domain, that's all real numbers. It repeats over and over and over again. Therefore, it is not 1 to 1. There are going to be multiple x values for a given y value. So therefore, we're going to restrict that domain. And this time, we're going to restrict tan to -pi/2 to pi/2. So exactly the same as what we did to sine. The only difference is we are not going to include the endpoints here, because the endpoints, -pi/2 and pi/2, they are actually asymptotes for tan. So when we draw out the graph of y is equal to tan x, it will look something like that. And then we have these asymptotes where this function is undefined, and that is at pi/2 and -pi/2. And if you remember, we actually have asymptotes at every odd multiple of pi/2. So 3pi/2, 5pi/2, etc. And the graph of tan goes through the origin. So we've restricted this to the domain -pi/2 to pi/2, not including those points. And now we have this 1 to 1 function, so we can find the inverse, being tan inverse. If we were to draw the graph of tan inverse, again, you can dot out the line for y is equal to x, and then you can draw in what that inverse function would look like, which is something like that. Okay, so this is y is equal to tan inverse. This time we're actually going to have these horizontal asymptotes. So it's not going to go above pi/2, and it's not going to go below -pi/2. Again, remember, our domain for our original function becomes our range of our inverse function. So that means, let's look at the domain and range of tan inverse. The domain of tan inverse is going to be the range of tan of x. Now, the range of tan is all real numbers. Okay, it goes all the way down to -infinity up to +infinity. So the domain is all real numbers. The range of y is equal to tan inverse is going to be the restricted domain that I had for tan, which is going to be -pi/2 to pi/2, not including those points, so I use parentheses. So when we go ahead and solve these problems, we need to remember what quadrants our outputs are going to be in. Okay, so for y is equal to sine inverse, okay, the angles that are going to be the possible outputs, remember now that we are going to have an input that's between -1 and 1 here for sine, and we're going to have an output that's an angle, and that output has to be for sine between -pi/2 and pi/2. Okay, so that's the possible range of values for y for an input of x, where x is going to be between -1 and 1. That means that if we were to look at our unit circle, the outputs, the results that I get, have to be within quadrants 1 or 4, okay? Because I can go, if we look at our unit circle, you can pull up a unit circle. If you pull up a picture of it, there is 0, there's pi/2, there's pi, 3pi/2, and then you go to coterminal angles, you're back to 2 pi. Pi/2 is up here, and then -pi/2, again, using coterminal angles, this time I'm going to go in the clockwise direction. So -pi/2 is down here where 3pi/2 is. So my possible outputs for sine inverse are going to be anywhere in quadrants 1 or quadrant 4. Okay. How about cosine inverse? Okay. The outputs of cosine inverse have to lie between 0 and pi. Okay, what does that mean for us with our unit circle? Well, if they must land between 0 and pi, it means that they must land somewhere in this part of the circle, which means that they must be in quadrant 1 or quadrant 2. Same goes with tan. Tan inverse, okay, again, has outputs between -pi/2 and pi/2, but just not including those values. So again, our solutions for tan inverse, our outputs, are going to be within quadrant 1 or quadrant 4, exactly the same as we had for sine inverse. Using this information, let's do some examples. Okay. First one that I'm going to look at is, what is sine inverse of 0? Okay. I am looking for a value, an angle, theta, that has to land within quadrant 1 or quadrant 4, such that sine of theta equals 0. Okay. Whenever you get a problem like this, just set this equal to theta, or you could set it equal to y. It really doesn't matter what variable you use. Okay, but as it's an angle, I'll set it equal to theta. Okay. Then we know, because it's an inverse function, I'm looking for sine of theta equal to 0. I'm looking for that theta such that that is true, where theta must be in quadrant 1 or quadrant 4. Okay. If we go to our unit circle, okay, we can evidently see, because sine of an angle, that is always the y coordinate. Cosine of an angle is the x coordinate of the terminal angle, of the terminal side of the angle on the unit circle. Okay, cosine's the x coordinate, sine is the y coordinate of the terminal side where it lands on the unit circle for that particular angle. So if we look at this, we want something that has a y coordinate of 0, okay, because we're looking for a theta such that its y coordinate on the unit circle is 0. That's right here at 0. Okay, at that point, You have an x coordinate of 1 because you're looking at a unit circle, it has radius 1. It has an x coordinate of 1, but because you are on the x-axis, its y coordinate is 0. So that tells me that theta equals 0. Next, we'll look at cosine inverse of 0. Okay. Again, set it equal to a variable. You can use y, theta, whichever one you want. And now I'm looking for a theta such that cosine of theta equals 0. And now theta has to be in quadrant 1 or quadrant 2 because I'm looking at cosine inverse. So I'm looking for a theta that lands in quadrant 1 or quadrant 2 such that now its x coordinate, okay, the x coordinate for the terminal side of theta, that is 0. Well, up here, if you go back to a real picture of this unit circle, at that point at pi over 2, you have an x coordinate of 0 and a y coordinate of 1. We land somewhere between quadrant 1 and quadrant 2, so we know that that is the case, and therefore theta is equal to pi over 2. Next, I'm going to look at sine inverse of negative the square root of 3 over 2. Okay. Again, set it equal to a variable. So I am looking for a theta such that sine of theta is equal to negative the square root of 3 over 2, and theta is in quadrant 1 or quadrant 4. Bearing in mind we have a negative here, that tells me that I must be in quadrant 4 because both x and y coordinates in quadrant 1 are always positive. So I know I have to be in quadrant 4 because that gives me a y coordinate and therefore sine of an angle. That is going to be negative. So I know I'm already in quadrant 4. Question is, what's the angle? Okay, remember I'm going to be looking for a negative angle. If I was looking for the positive, if you look at a unit circle, if I was looking for a positive angle that was in quadrant 4, you would end up with 5 pi over 3. Okay. So if I look at the unit circle and I pick out the point that gives me a y coordinate of negative the square root of 3 over 2 that lands in quadrant 4, I know I've got 5 pi over 3. The problem is my output for sine inverse is between pi over 2 and negative pi over 2. At the moment, I have an angle that is even bigger than pi over 2. So what I need to do here is I need to find that angle that's coterminal to this angle, so it's at the same point, but it's going to be negative. Okay, so what I'm going to do is if you subtract 2 pi from this, you end up with the negative version of this angle, where you've got the angle that's coterminal to it, so it's going to have that same coterminal side, but now it's going to land inside this set here. So if I do that, I end up with negative pi over 3. How about cosine inverse of 3? Okay, again, set it equal to theta. Tells me that cosine of theta equals 3. There's a problem here. Okay. Cosine of an angle is always between negative 1 and 1. You can't have cosine of an angle equals 3. Therefore, this theta is undefined. Okay. It is not possible to find a theta such that that is the case. I'm going to do a quick tan example as well. So let's say I'm looking for tan inverse of negative the square root of 3. Okay. Again, set this equal to theta. So I'm looking for tan of theta is equal to negative the square root of 3. And again, theta is in quadrant 1 or quadrant 4, okay? It has to be between negative pi over 2 and pi over 2. Whenever you get a problem like this, what I would do is convert it back into sine and cosine, because it's way easier to deal with, and we can use our unit circle and those xy coordinates in order to figure out theta. So I want a theta such that sine of theta over cosine of theta is equal to negative the square root of 3. And that theta has to be in quadrant 1 or quadrant 4. Okay. If you go ahead and look at the coordinates in order to find something in quadrant 1 and quadrant 4 such that this is the case, you will find that there is an angle that lands in quadrant 4 where you have the sine of the angle is negative the square root of 3 over 2, and the cosine of the angle is 1/2. If I take sine over cosine, so the y coordinate divided by the x coordinate, the 2's cancel out. I end up with negative the square root of 3 over 1, which is just negative the square root of 3. Okay. I need the theta for which this is true, and it actually turns out to be the theta from our last problem. Okay, it ends up being 5 pi over 3, which we said because we need it inside negative pi over 2 and pi over 2, we're going to write that as negative pi over 3. We're going to subtract 2 pi from that, find that coterminal angle, and it gives me negative pi over 3. So whenever you get one of these problems with tan, always convert it to sine and cosine, and then look for coordinates on that unit circle such that when you do the sine divided by cosine, or the y coordinate divided by the x coordinate, you do get that value. But make sure that you are only looking in quadrants 1 and 4, because tan is only defined, or tan inverse is only defined there. I'm now going to look at the composition of some of these trig functions with an inverse and a trig function to see the values that we get out. The thing that you must remember with this is the domain and range of those inverse functions. That is very important here. Okay. I'm going to do a few examples to show you how this works in action. If we look at, for example, sine inverse sine of 11 pi over 6. So I've got the inverse of a function combined with the original function of a value. Now you would think, because I've got the inverse in the original function, they would almost like cancel one another out and you would get 11 pi over 6. But because of that restricted domain and therefore that range of the inverse function, you actually end up with a different answer to what is in there. Okay. Let me show you how this works. So if you look at a unit circle, always work from the inside out. Sine of 11 pi over 6 is going to be the y coordinate at 11 pi over 6, which is negative 1/2. Okay. Now I need to find sine inverse of negative 1/2. So I'm looking for the theta such that sine of theta is equal to negative 1/2, and theta is between negative pi over 2 and pi over 2. Well, if I go ahead and look at my unit circle and find the value that is between negative pi over 2 and pi over 2, you will see that it's got to be coterminal to 11 pi over 6, but the problem is 11 pi over 6 doesn't land between negative pi over 2 and pi over 2. So I have to find the angle that's coterminal to it that does land between those values. So that tells me it's negative pi over 6. So with a lot of these, you're going to be dealing with these problems where you have to worry about which quadrant you're in and make sure that you actually have a value that is in the correct range here. Okay, if you end up with a value that is outside of wherever sine inverse is defined, or the range of sine inverse, if you end up with a value that's outside of that, you know you've gone wrong somewhere. So you really have to pay attention to the domain and the range of sine inverse. Okay. Let's do a cosine problem. So this time I'm going to look at cosine inverse cosine of 7 pi over 6. Okay. 7 pi over 6, that's in quadrant 3. I'm pi over 6 past pi. So if I look at what cosine of 7 pi over 6 is, I am looking at the x-coordinate of that terminal side of that angle on the unit circle, and I get negative the square root of 3 over 2. Okay. Now I'm looking for cosine inverse of negative the square root of 3 over 2. So I'm looking for a theta on my unit circle such that cosine of theta is equal to negative the square root of 3 over 2, and theta, because we're looking at cosine inverse here, has to be between 0 and pi. It's negative, I know, because I'm looking at a negative x-coordinate here. I've got to be in quadrant 2. So if we go ahead and look at the x-coordinates such that the x-coordinate for the terminal side of that angle is negative the square root of 3 over 2, I end up with theta is equal to 5 pi over 6. So again, I've got the inverse of a function with the original function itself of an angle. You would think that you would get the angle back and that the functions would cancel one another out. They don't, okay? You end up with a different angle. So please bear this in mind. It's all due to that domain and range being restricted. Okay. I'll do one with tan, so we'll do tan inverse tan of 7 pi over 6. Tan of 7 pi over 6, you can find that by doing sine of 7 pi over 6 divided by cosine of 7 pi over 6. That was how, either that or type it into a calculator, but this is how I would do it. Okay. And you should end up with 1 over the square root of 3. Okay. Then we've got to find tan inverse of this. So I am looking for a theta such that tan of theta is equal to 1 over the square root of 3. And theta, again, because we're looking at tan inverse, has to be between negative pi over 2 and pi over 2, but not including those values. So I'm looking for somewhere in quadrant 1 or quadrant 4, such that when I do the y-coordinate divided by the x-coordinate, hence sine divided by cosine, I am going to get 1 over the square root of 3. Okay. That would be the point where you get a y-coordinate of 1/2 and an x-coordinate of the square root of 3 over 2. The 2's would cancel out and I would end up with 1 over the square root of 3. So where I have a y-coordinate of 1/2 and an x-coordinate of the square root of 3 over 2. They're both going to be positive here because tan is positive. Okay, and I don't have to worry about them both being negative because that's in quadrant 3. So that tells me, if I look at the angle for which that is true, that would be pi over 6. Let's look at what happens if I do the inverse of one function with another function. This time I'm going to look at cosine inverse of sine of negative pi over 3. Okay. Sine of negative pi over 3, that's, if you look at the coterminal angle to negative pi over 3, you're going to get 5 pi over 3. So it's sine of 5 pi over 3, which is negative the square root of 3 over 2. Now I've got to find a theta such that cosine of theta is equal to negative the square root of 3 over 2. And because I'm looking at cosine inverse, theta must be between 0 and pi. Okay. I'm going to be in quadrant 2 here because I know that I've got a negative for my x-coordinate. This is a negative. So I'm looking for the angle that gives me an x-coordinate of negative the square root of 3 over 2, which ends up being 5 pi over 6. Okay. So these work in exactly the same way, Just always make sure when you look at that inverse function, make sure that you get an angle that is between the correct values. One other type of problem that you might get is where they do the inverse function on the inside. Well, let's focus on this inside part first, okay? This is going to equal theta, so I'm looking for a theta such that sine of theta is equal to 4/7, okay? That particular coordinate, or y coordinate, as we're looking at sine, that is not on the unit circle. You are not going to find that fraction on the outside of the unit circle. So how do we do this? Well, we're going to take it back to our right-angled trigonometry. Okay. If I draw out this triangle, put theta here, remember sine of the angle was opposite divided by hypotenuse. So the opposite side to the angle is going to be 4 and the hypotenuse is going to be 7. I don't at the moment know what the adjacent side is. I can find that by just using Pythagoras' theorem. So I can do 4 squared plus x squared is equal to 7 squared, telling me that x squared is going to be 7 squared minus 4 squared, which is 33, and x is going to equal the square root of 33. Okay. Now, if I come back up here, okay, I set theta to equal sine inverse of 4/7. So I'm looking at cosine of theta. Well, I can figure out cosine of theta from my triangle now. Okay. I have that x value now. Okay, I know what this unknown is. So I can say that cosine of an angle is always the adjacent divided by the hypotenuse. So cosine of theta is equal to the adjacent divided by the hypotenuse. And that is the answer. Okay, so what you do here is you set the inside of this function, so sine inverse 4/7, you're going to set that equal to some angle. Then you're going to use the right angle trigonometry in order to draw out that triangle, find the other side, and then you can find cosine of theta. Okay, you've set that inside equal to theta, you can then find cosine of theta. Okay. We'll do one more of these. So let's say I've got sine of cosine inverse of -2/5. Okay. Again, I set this inside part equal to theta, so I'm looking at cosine of theta is equal to -2/5. So this time, when I draw this out, okay, again, the negative's just going to deal with a directional thing here. You don't have to worry about that because when you square it, it's going to become positive anyway. But let's say I set this equal to theta, then cosine of an angle is always adjacent divided by hypotenuse. So my adjacent is -2, my hypotenuse is 5. Always set your hypotenuse to be positive. Okay. Then I need to find my unknown side, so that's going to be -2 squared plus x squared is equal to 5 squared. So that tells me that x squared is going to be 5 squared minus -2 squared, which is 21. So x is equal to the square root of 21. So now, if I look up here, I get sine of theta. Sine of theta is going to be opposite divided by hypotenuse, which is just the square root of 21/5.